Welcome back, business calculus students. In this section of our midterm review videos, I'm going to be working problems 20 through 26. We'll be dealing with our rules of differentiation, including product, quotient, and chain rule, but as they apply to exponential and logarithmic functions. So on problem 20, notice we're differentiating an exponential function. The rule of thumb for differentiating an e is to make a copy of it exactly as it appears and then multiply by the derivative of the exponent. So for this function, we need to filter that constant coefficient through to the derivative like we normally do. And then we're going to make a copy of the e exactly as it appears and then multiply by the derivative of the exponent. Now watch your levels here. Make sure that the e and the 8x are all on one line and your exponent is clearly in the exponent position. Make it readable so you understand the nature of the factors that you're dealing with. To simplify this, we can multiply our little terms together and move them to the left. We would end up with negative 16x e to the negative 4x squared. Piece of cake on that one. On problem 21, again, we're dealing with an exponential function, but notice it's in the context of a product. We have the product of two functions on number 21. That means we're going to have to apply the product rule. So let's do that. Following our pattern, same times derivative plus derivative times same, we end up with our first factor, 7x squared minus 14x plus 14, times the derivative of the second factor. Here we have arrived at an exponential function. When we differentiate, we make a copy of the e exactly as it appears, and then multiply by the derivative of the exponent. That's according to our chain rule. Continuing with our product rule, remember the pattern is same times derivative plus. Now we're ready to differentiate our first factor. Happens to be just a polynomial. Its derivative is 14x minus 14. And finally, to complete the product rule, we have our exponential function on the end. The calculus part is done. We can check that off. Our next goal is to simplify what's left. So I observe that I have two terms, one on either side of that plus. So I'm going to inspect these two terms to see if they have a greatest common factor. At this point, the obvious part of the greatest common factor is e to the negative 5x. Let's extract that and see what's left. So writing our GCF over here to the left, we are taking an e to the negative 5x out of both terms. Let's see what's left. Well, taking the e to the negative 5x out of that first term leaves behind 7x squared minus 14x plus 14, and we have that little factor negative 5. Plus, second term, when we take out the e to the negative 5x, that leaves behind 14x minus 14. Let's go back and simplify by distributing the negative 5 into this set of parentheses. We obtain e to the negative 5x. Demoting our brackets to parentheses, we have negative 35x squared plus 70x plus, that last one should be a minus 70 plus 14x minus 14. And then combining like terms, we have e to the negative 5x times negative 35x squared. The 70x and the 14 combine to give us 84x. And then the minus 70 minus 14 combine to give us negative 84. So we've successfully combined like terms. However, do you notice in that set of parentheses, we have another greatest common factor? It happens to be 7. So let's take out a 7 and we will arrive at our final answer. So taking a 7 out of that polynomial and including it here on the left with our already extracted GCF e to the negative 5x, we end up with negative 5x squared. Remember, I'm dividing each of those terms by 7. So we get negative 5x squared plus 84 divided by 7 is 12x, and then minus 12. So we have applied the product rule, and then simplified as far as possible. Problem number 22 involves an exponential function again, but we will apply the chain rule in this case. Notice we have a function of z raised to a power. So the first thing that I want to do on this problem is apply the power rule. Now I'm going to cross my z's so they don't look like 2's and confuse all of us. Okay? So applying our power rule, we take the power down in front, keep the base the same, and then decrease the exponent by 1. All right, so that takes care of the outside function, but the chain rule says now multiply by the derivative of the base. That gives us 8 plus, now notice to differentiate the e here, we make a copy of the e and then multiply by the derivative of the exponent. Okay? So cleaning up that last element there, just going to copy these down. We have 8 minus 2z e to the negative z squared. Remember, it's easy to take those little monomial factors to the left of the exponential to make it readable. Now, we have differentiated it, but it's not completely factored. Notice here we have a greatest common factor of 2. So we could take out one more common factor here, and I'm going to move it all the way over here to the left with my little constant multipliers. This one's just hanging out, being patient. And dividing each of these terms by 2, we have 4 minus z e to the negative z squared. So our final derivative is 8 times 8z plus e to the negative z squared quantity cubed times 4 minus z e to the negative z squared. All right? Moving on to number 23. Let me give you a tip on number 23. Notice we're getting into a couple of problems where we're dealing with the derivative of a natural log. Remember, when you differentiate natural log of x, the derivative is simply 1 over the argument. However, when you differentiate natural log of a function of x, where u represents a function of x, you still put the argument in the denominator, but you put the derivative of the argument in the numerator. Okay? Now, before I actually apply that to this problem on number 23, I'm going to rewrite the function. I'm not differentiating, so I'm going to call this y. I'm going to rewrite that radical, the square root, as a 1/2 power. Okay? From rules of logarithms, we know that if the argument of the logarithm has an exponent, we can move that exponent down in front as a coefficient. Please understand here, I'm not differentiating. I know it feels like the power rule because we're moving a power down in front, but I'm applying a log property. The purpose of that is to simplify the function before I differentiate it. Now I'm ready to differentiate it, so I'm going to call it y prime. Okay? Now I have a constant multiplier 1/2. That always lands in our derivative. Now I'm ready to differentiate natural log of x plus 6. So I'm going to take the argument of the logarithm, that's the part in parentheses, and put it in the denominator, and the derivative of that argument in the numerator, which in this case is just 1. So that's that, piece of cake. If you deal with that radical up front by simplifying with log properties, your derivative is very simple. So we end up with 1 over 2 times x plus 6. Okay? Problem 24 is also dealing with a natural log function, but notice it is in the context of a quotient. So which rule should we use? Quotient rule. So let's plan out our quotient rule here. A good habit is to square the denominator first so that you understand which term to begin with in the numerator. That way we'll get our numerator in the right order. So we have the denominator 2 plus 3x. Now we need to multiply by the derivative of the original numerator. So the derivative of 2 times natural log of 3x is constant coefficient 2 times the derivative of natural log of 3x. Well, we're going to put the argument of the logarithm in the denominator and the derivative of that argument in the numerator. Continuing with our quotient rule, remembering that the quotient rule requires a minus, we're ready now to differentiate the denominator. The derivative of the denominator 2 plus 3x is very simply a 3. And then we'll multiply by the original numerator, which was 2 natural log of 3x. So the calculus part is complete. Now we need to work on the algebraic simplification. First thing that I spot here is 3 divided by 3. Those will cancel. And then, do you notice we have a complex fraction? That is, we have a fraction in a fraction. We need to take care of that x in the denominator. Anytime you've got a fraction in a fraction, you need to reduce it to just a double-decker fraction. The easiest way to do this is to multiply the top and bottom of your main fraction by the LCD, lowest common denominator. In this case, I'm going to multiply by x over x. Be very careful in the numerator here. I'm taking x and I'm multiplying it by 2 terms. So I'm going to need to distribute this x. Notice when I distribute it to this first term, it cancels that x in the denominator, which is what's making it a complex fraction. So my denominator is gone. I'm going to reverse these 2 terms, make it readable. We have 2 plus 3x. Okay? Distributing the x to the second term there, we have minus 3 times 2, which is 6. The extra x that we're multiplying here, and natural log of 3x. And in the denominator, we have x times 2 plus 3x quantity squared. Okay? Now let's compare our 2 terms on either side of that minus. On the left side, I've got this term. On the right side, I have this term. Do you notice they have a 2 in common? Well, we can factor out the 2 and we will arrive at our simplified answer. So factoring out the 2, that's going to leave behind this term 2 plus 3x. Taking it out of our second term here, 6 divided by 2 is 3. So we have 3x natural log of 3x divided by denominator x times 2 plus 3x quantity squared. Okay, I will accept various forms of the answer. So if yours is expressed a little differently, that's fine, but do make sure that you reduce that complex fraction. Okay, number 25 is an exponential function, but notice how it's different. We have not e to a power, but some other constant to a power. So you'll definitely need to remember this formula. When you differentiate some other base than e raised to x, you make a copy of the exponential just like we did with the e, but you have an extra factor that is multiplied by natural log of the base. So the derivative of 2 to the x following this pattern, we would make a copy of the exponential as is, and then multiply by natural log of the base. Now that is a super easy problem on one condition. That is, you know the formula. If you don't know the formula, it's going to be really tough to find that derivative. So make sure you memorize that formula. Make that problem a gimme problem on your midterm exam. Okay, same thing with number 26. Notice we're not differentiating natural log, which is base e. We're differentiating log log, that's base 10. So when we differentiate with respect to x, log with some base of a function, we're going to have an extra adjusting factor. We're still going to apply the process where we take the argument of the logarithm and put it in the denominator, but we're going to have an extra factor here, natural log of the base. Okay? If, as in this case, the argument happens to be a function of x as opposed to just an x, We're still going to follow that practice where we put the argument in the denominator and the derivative of the argument in the numerator, but we do have this extra adjusting factor in the denominator. Okay? So applying this second formula to this problem, y prime would be, well, let's start with the arguments. We put the original argument in the denominator and we multiply by the derivative in the numerator, but because it's log base 10, we're going to adjust it by putting a natural log of 10 right here. Okay, remember the base is not written. If it's not written, it's understood to be base 10. Reducing our 5's here, we end up with y prime equals 1 over, I'm going to put the little x term to the left of that natural log so that it's easy to read, x natural log of 10. So memorize those formulas, practice those for your midterm. Take a little break. We're almost done. We have just a few problems left of the midterm review, which we'll work in the next video.